The implementation just use all the structures we have, all the functions we have implemented before, but with more complex practical considerations. Okay, so it may look a bit lengthy, but there's no difficult technology here. We can understand the structure step by step. Okay, you will be provided with a block of code like that, and we can start reading. They are organized in 3 main classes and 1 helper class. This helper class is what we use to store all the options and other useful stuff. So it's just to help implementation. We ignore this for now, and we will refer to the information here, explain them later. Look at the self-attention code here. From a starting point, we allocate the transformations which is needed for the attention computation, which is just as we have discussed. The K transformation transforms C dimensional feature vectors to another C dimensional feature vector. So does the query, so does the value, and after the attention computation is finished, we will use the output transform. Okay, and we allocate the mask for the causality, which allows token only attend to the token before it, using the mask as discussed before. Here, the maximum length of the sequence is given as a parameter in the configure, and the configure is of course one object of the configure helper class. Okay, the forward process of this is just slightly more difficult, more complicated than we have already been discussed. I forgot these 2 parameters. They are called dropout. They will help the training of the model. We will come to them very shortly when we discuss the forward. And when it is given a sequence, this attention mechanism first determines the size of the sample. The batch size means how many documents or how many sequences there, which is not very relevant, but it's necessary thing to help us to get batch processing of data. And this is the actual length of this token sequence, and this is the length of the feature vectors. Okay, and the feature vector is called the embed dimension. This must be this must agree with when we have set up the model. So we employ some of the assertion to ensure everything is working. To be more accurate, actually, if we have something wrong here, the thing won't work, and we do not really need to worry about we have make errors here. If we make errors here, the computer will automatically stop, but the assertion helps anyway, because when we make errors here, we of course next step is to correct the error, and those assertions make it very easy to identify what's going wrong and what's to be rectified. So in the next step, we will split the information and input into different parts. For each feature vector, we split it into some number of so-called heads, and we will compute the attention among those heads. Okay. We do that for all three parts of the all three parts that participate the attention computation. Okay, and this is where we figure out if the number of heads and the subdimension in each head, when they combine together, the multiplication is just to be the right number of the original dimension, the dimension of the original feature vector. Here we perform the transformation using the K matrices, which we initialized here, and do the query, do the Q value transformation, and after that, so look, this will return us another tensor, and this dot following the return tensor, we just do the computation following this result. Okay, this is a very common way of writing a sequence of related computation steps. And here we view the tensor in the way that we look at the attention in different heads, and here is the transpose we have discussed before to put to reorder the information so that we, in the next step, when we do the matrix multiplication, we are combining, we are considering the attention between different parts of the data rather than that between different heads of the same part of the data. So here we compute the attention. I think I'm employing the torch matrix multiplication. This is the same as if I'm using this symbol. Okay, like OP operand 1 times operand 2. Here you can use torch matrix multiplication, and so they are doing the same job. And then we can mask the attention so that it represents a causal relationship. I think here we need a little bit technique here, because the mask is only one matrices, but here we will need to apply this masked feeling, masking the attention matrices for all the heads among all the documents. So we add 2 dimensions before the mask, and we only need the first number of seconds part of the mask matrices. So maybe we can make it more explicitly. So the mask will be used in this way. We have mask matrices here, which is filled only for the lower part. We take it only this part because this is for the maximum length of possible sequences. But actually, for this bunch of the data, this batch of the data, we only have this size of sequence. So we use only this size. And because the data comes with maybe several documents, okay, so for each of the documents, there are several parts, and for all the parts, several different parts. For those parts, we split them into different heads. So for all the heads, we will have their respective attention matrices, and we will apply this to all the respective attention matrices and to all the documents. So we have 2 additional dimensions here. Okay, and lastly, we do the output computation, and finally we do the output. Here there are two so-called drop operations. That means we randomly take some portion of elements in the tensor of question. The elements that to be taken is just randomly chosen from there, and we turn those elements to 0. This seems to be has headers and arbitrary. It doesn't look like helping the model to learn, but it turns out this is a good regularization method to help the training process from overfitting to the data when the model is complicated. So it's often adopted technique. This does not contain any learnable parameters. This is just an operation to disturb the computation of the model so that to prevent it to concentrate too much on the observed data, and which cause, well, in some sense, roughly speaking, overfitting. So that is why we have these attention dropout layers, and these dropout layers, to be reminded, only works when we are training the model. When it comes to the test time, when we have a trained model and we want to deploy the model for use, we do these layers will not apply. These layers implemented with some automatic mechanism. They know, by telling that the model is in the training or the deployment test mode, those layers can automatically adjust their behavior. Okay, so and there is another such layer after the the output transformation. So this is implementation of causal attention.